So yesterday at the speaker dinner, where Teresa got a lot of the information that she just shared, I gave a spontaneous lightning talk on this topic because one of the other speakers who has a talk at this point exactly wanted to know more about it, and so I didn't have slides and I was fairly drunk, so this feels a bit like cheating right now. Yeah, but it's cool. All right, so what I want to share today is some insights about, what makes the game of poker really complex and challenging for AI, and then introduce you to some of the building blocks that go into solving it at superhuman level, right? And at the end, I will show you some demos of what we've built in the last couple of months. All right. So before we get started, just a few words about Skymind. So Skymind has originally been founded in 2014, and by now we have more than 200 employees worldwide, and we're a globally distributed, fully remote team of deep learning experts, at least on the engineering side. And we also currently launching a new product line called Conduit, which you find in the top right, which is derived from the French word for pipelines. And what Conduit does for you is give you an easy way of deploying pretty complex machine learning pipelines, right? So I can't really talk about this, but just to let you know. All right. Another thing about Skymind, I mean, Teresa already mentioned it from my perspective, but Skymind is a fairly active open source contributor, right? So just to give you two examples, Deep Learning for J, which is also created by Skymind and maintained by us, has, of course, the top contributors to it. And overall, we contributed more than like 1 million lines of code to open source. And that also includes Keras, which you see on the right. So we're not just maintaining our own software, but we're also putting work into other frameworks. Right. OK, and the last thing I want to mention before we get into the nitty-gritty of poker is that we just released a new version of HyperOpt, which is a project I maintain in my free time, essentially. And for the data scientists among you, you might know the software. So it's a fairly popular distributed asynchronous hyperparameter optimization tool. And the innovation that you find in the new release is that it now easily scales out on Apache Spark. So if you have a Spark cluster in your company or just floating around, and you have a hyperparameter optimization problem, you can essentially scale it out to that Spark cluster by just changing one line of code, which is pretty cool. So, and this whole project of integrating Spark with HyperOpt has been a collaboration with Databricks. So you find HyperOpt under this URL in the lower right, and we also have a fairly new auto-generated documentation for it. Cool. All right, so poker AI. So poker is a fairly complicated matter in its own, and poker AI is fairly complex as well, right? So let's have a look. If you look at the game of poker from an AI perspective, it has been kind of a poster child application since the early days of AI. So if you look back to the McCarthy area in the 50s. Poker is always mentioned. So it's not just a game AI milestone to achieve, but it's a well-known AI milestone in general. Yeah. And what's interesting about it is that we've seen very little progress in terms of actually solving the game. So you might have heard about breakthroughs in Superhuman chess or Superhuman Go, and poker is kind of a different animal, and we will talk about this. So why poker is so hard? Yeah, so it's a very, very complex multiplayer game, but before 2019, the only progress that has been made actually was in two-player variants. So And I mean, this list is not comprehensive, so this is not like a history of poker AI, but it is certainly so that before the 2000s, you don't find much in terms of actual poker games being solved, right? There's many variants, but none of them are really impressive. You know, it's just very small games that could be solved until then. So with Cepheus in 2015, we see that two-player limit hold'em. So this is the variant where you can only bet a fixed amount for some rounds, and then it's limited to that. This has been solved, and this is still a fairly small game, right? So it only has like 10 to the 13 possible moves throughout the whole game. Whereas if you look at no limit hold'em, the two-player version, which has been solved with Libratus in 2017 by Carnegie Mellon University. This game has around, the number of atoms in the universe squared possible moves, right? So 10 to the 80 would be the atoms, and you see that this has a complexity of 10 to the 165. And for reference, Go has 10 to the 170, I think. So, and the breakthrough that I want to talk about mainly, but all the other earlier versions use pretty much the same techniques, but in a different way. So it's worth considering anyway, is Pluribus, which has been published in July 2019. It's a collaboration with Carnegie Mellon and Facebook, and actually the authors of Pluribus are also the same as Libratus. All right? And, well, this is a fairly impressive system in many regards. So first of all, it beats the by far most popular version of poker there is, right? So it's multiplayer, usually 6-player, no limit Texas Hold'em, and not only does it beat the pros, it beats the top pros decisively. Yeah, so it beats World Series of Poker winners decisively, like by 50 millibig blinds per game. What's also quite interesting about it is that oftentimes these days AI is conflated with deep learning, and it's quite interesting to see that Pluribus in itself does not use any deep learning. So, and it's kind of a bit ironic also that like a deep learning engineer would talk about a system that doesn't have any deep learning in it. So to compensate for it, I wear my most geeky deep learning shirt I could find. Right. I think the third point here on this slide for Pluribus is that it only costs $150 to train on AWS, I think the authors state. That, of course, implies that you have a very efficient system that can pull it off. You know, I mean, you need to build a really strong Pluribus first, but the training phase only costs a few $100, right? If you compare this with other AI breakthroughs like DeepMind's AlphaGo, that has cost millions in training, right? So this is affordable, yeah? So it's a new AI that's not deep learning, and that's also not that resource hungry. That's really cool. Plus, the techniques used there are pretty much general purpose, right? So none of the techniques used are specific to poker, right? You could apply it to other domains as well. For instance, negotiations. So what makes poker so hard? So first of all, let's just look at games in general, maybe finite games, right? So if you want, you can view any game. It doesn't always make sense. You can view it as a tree. It has a certain width that describes the number of moves per player. And in No Limit Texas Hold'em, this width, or the branching factor that we usually talk about, is about 20,000. So it's quite huge. And the depth is usually the number of moves per game. Like, if you know a bit of poker, at first it seems like poker can be really small in terms of depth. But if you look at the 6-player version, and everyone can raise and re-raise in practically every round, so you kind of have accumulate quite a lot of moves during a game. Okay, so it's actually more complex than you maybe intuitively think about. Right. So and how it usually looks like in any game. I mean, pick your favorite game, right? So chess maybe. You start from the top, and the first player takes an action, and then the second player takes an action. Third and fourth, or if you're just two players, you alternate. You take new actions, right? What this amounts to is you get a certain action history. That's what happened in the past. And you arrive at the current state from which a subgame derives that eventually ends at the terminal state, some terminal state, right? And now we're talking about perfect information games just to get started. Poker is all about imperfect information, right? So let's see what we have there. So in perfect information games, you have all the information you need to make an informed play, right? There's nothing out in the dark. And that in particular means that you can, in principle, evaluate your current position. And not only that, you can kind of forget about the history. Like if you remembered what happened, you don't have to go back and challenge what you did. You can just solve the sub-game, you know? Like to give you a really, really simple example, there's this chess example. Everyone who's ever played chess knows Scholar's Mate, right? It's a checkmate in 4, and you just have to move your queen there, and the game is over. I don't have to know anything about what happened before, right? I might know, I might be able to infer it, but in this particular situation, I can just look forward. Right. Another quite interesting example, apart from chess, is Go, which, like in the initial version at least of DeepMind's AlphaGo in 2016, actually the way it was solved on a very high level was quite similar to what we've seen in chess before. But I mean, of course, there's differences. Primarily, you use the technique of deep learning in 2 places. Namely, to evaluate positions and to make guesses for next moves that you can use for guiding your search through the game tree. All right. But it's also interesting to point out that if you forget about the search component, yeah, which has nothing to do with deep learning in particular, if you don't do that, you don't reach superhuman level. You reach really strong amateur to low professional level, but it's not superhuman in the same way. So real-time search is a crucial component, and the same holds true for chess AI as we know it, right? So we can't just neglect that. All right. Cool. All right, moving on to imperfect information games. So imperfect information games, yeah, well, it's kind of obvious on an abstract level, but you don't have all the information you need. There's certain things you don't know about, right? So in a game of poker, even if you've never played it, it's usually the way that you hold cards that you don't share with others, and the others hold cards that you don't know about, right? So this is imperfect information. And that has grave consequences for how to solve the game. In particular, all the techniques that we know from solving chess and Go simply don't work. At least not straight up. Yeah. And well, I don't actually know what game state I'm in. You know, I have a variety, like a set. We call this information set, that consists of game states that I could be in. You know, because I simply don't know the cards of the other players, right? And that means, in turn, that solving subgames is not enough because I'm not even sure in what subgame I'm in. All right. So what I have to do is, when I do something like position evaluation, if I don't even know what game state I'm in, how can I evaluate my position? It's not that trivial, right? So I have to be creative about that. And one part of that is that I need to consider a belief distribution about what other states my opponents are in, and what strategies they take, right? If I don't have that, I have no way of knowing what's going on. All right, and well, it's it's also worthwhile to point out that most real-world interactions is actually like that, right? I don't always have the full information on the table. Yeah, that's why I brought up the example of negotiations, right? Like negotiating salary is one such example. You operate from a certain position, and others have other opinions, and you kind of meet in the middle. But this is kind of a game of poker, if you will. Okay. Right. And maybe the last point, what you have to do here is you have to consider counterfacts. So I have to really carefully think about what my opponents could have done or what I could have done if the game state or the situation I'm in were actually different, right? Because I simply don't know. So I have to consider all of those counterfacts. All right. How do we approach imperfect information games in general? All right. To approach it, so we'll talk about one crucial technique called counterfactual regret minimization. But before we do so, let's try to play a very, very simple game of poker, right? This is called coon poker, and it has been invented in 1950s, right? It's actually a very, very simple game that we can play together, you know? In coon poker, this is a two-player poker game, right? And there's 3 cards in general, in total. You pick a card, and I pick a card. And whoever has the highest card wins. But of course, it wouldn't be poker if we weren't betting for it. So each of us, to enter the game, has to pay $1, right? And what we can do is, you can raise once, $1, and I can call you, right? This would increase the total pot to $4. So if indeed you were to hold the highest hand and we both raised, you would win my $2, right? If we just don't raise and just check, the pot remains at $2, and if I lose, you win $1, right? So it's quite a simple game. And you're not allowed to raise multiple times or anything, right? Okay, let's do that. But before we do so, let's introduce a few terms that are crucial for poker AI. So regret, quite intuitively, is just a reward that is lost by not choosing other options, right? So if I could have folded a really weak hand, probably I would have lost less, right? Or if I could have raised a really strong hand, maybe I could have squeezed more out of you, right? So regret is just the difference between what I have and what I could have had. And then the technique of regret matching is you keep track of how much regret you have accumulated across a series of poker games, and you play proportionally to your regret. Like if I say, all right, last round, I lost a lot of money by not playing this, by not raising. Maybe proportionally to what I regretted, next time I play this option, right? And then counterfactual regret, based on that, is the regret you incur by choosing other options, by not choosing other options throughout the game, right? There's several betting stages that you could have turned otherwise. Maybe in a full game of poker, pre-flop, you could have dealt with this differently. And so it's taking into account altering the game in hindsight, right? You choose other options that you otherwise wouldn't have taken. All right. Let's say you have a king, and I have a queen, right? The king is the higher card, so you win either way, unless you fold, right? And I have the weaker hand, but I still can enter the game. I don't know which card you have, right? So it could be that I think that you hold a jack, right? And I can beat you. So it wouldn't necessarily be a really good idea for you to play your king really strong and just raise every time. I could infer from your behavior that you hold a really strong hand, right? So for the king, it might make sense to slow play a little, and trick me into thinking that that you actually have a weaker hand. All right. So, all right, you hold the king, I hold the queen, and it's your move first, and we call you the traverser for this round. And what we do is we track all of your regrets. And in the beginning, you don't have any regrets. So I've put this regret vector up there, and that has 2 zeros because both choices I have, namely checking and raising, I don't have any regrets. We haven't played yet, right? And what we do is you choose an action, whatever, right? And I am your opponent, and I choose actions randomly. All right. All right. And what we will do is we will explore all the alterations, all the different choices you could have taken in hindsight. All right. Those are the counterfacts. Right. So let's continue. Let's say player 2, that's me, right? I raise you with my queen, right? Because I think, well, you called previously, I raise you, I think you have a jack, maybe I can force you out of your hand, something like that. Or maybe I can even get you to raise again, I win $2. So I raise you, but you definitely have the stronger hand. But let's say because you're new to the game, you don't know what to do, all right? So you actually fold the hand. That means you get a reward of -$1 because you just lost your dollar you entered the game with, right? But you also could have raised, right? So what happens if I raise? If I raise, I get your $2 in the pot, right? So my hypothetical reward, my counterfactual reward there, is $2. And that means my regret, the difference between what I could have gotten and what I have, is actually $3, right? So I update my regrets to 0.3 because raising would give me $3, right? All right. Let's consider other counterfacts, right? I'm done with the below node because there's no more actions to explore. But at the very top, I also could have raised to begin with, right? What would happen then? Right. We choose a random action. So I choose a random action. You raise me. I suppose you have a king. I fold, and you win $1, right? And we only sample one of those actions from you. So what we can do is we backtrack or backpropagate the hypothetical reward that you could have gotten, right? Which is $1 here. And now you see at the top node, P1, player 1, that's you. The difference between your ideal scenario here, winning $1 and losing 1, is actually, the difference is 2, right? So the regret is 0.2. Okay? So next time, when I'm in this situation, I hold the king, I don't know what you hold. Because I lost so much, I pretty much played the worst choices I could have. You would then, proportionally to your regret, choose the other option, right? So next time with your king, you would certainly, at the top spot, you would definitely raise. Okay? Okay. So this is counterfactual regret minimization, or a version of it, let's say. And in the next round, I would become the traverser, and you sample random actions. And we do this, well, for a lot of iterations. And we update our regrets accordingly and run the simulation for a while. So to give you an impression, even for this tiny game, you need about 50,000 iterations to make it converge to something meaningful, right? And what you do at the end is you play the average strategy over all the runs you've taken. So just to give you an example here, right. Maybe I end up with a regret vector of 793 at the top node, and I don't know what you hold. But that means I would raise you 93% of the time. But if I don't, right, then we're in this bottom left scenario where no matter what you do, I will always re-raise you because I hold the stronger hand, right? So this would be the outcome of counterfactual regret minimization. All right. Cool. All right. Now, this is just one key technique used in Pluribus, right? This superhuman multiplayer poker AI. And so let's talk about a little bit, just 2 slides, how building Pluribus would look like, at least in principle. All right. So in the first phase of 2 stages in Pluribus, you do counterfactual regret minimization or a pretty complicated version of it. But you realize pretty soon that the game is simply too large, right? I mentioned it initially. It's like the number of atoms in the universe squared, amounts of actions. So that simply won't fly. Like if I need 50,000 iterations to solve Kuhn poker, that's simply not feasible, right? And the solution is to use something called abstractions. And there's 2 types of that. So there's action abstractions, in which you group the amounts, the actions you can take, which essentially means you can call, fold, and raise in certain buckets, right? And you restrict those actions. And the second one, maybe more importantly, is you group similar hands. And the way of actually doing that, how to group hands, is not easy. So like there's a certain mystery about how the authors of Pluribus actually did that, but they refer to a lot of papers that that to a certain degree allude to what they might have done, but it's not quite clear. But what you can do, for instance, just a similar simple thing is you can compute something called expected hand strength. Yeah, even if I don't know what my opponent's cards are, I could say, given my cards that I hold, on average, how would I fare? You know. And this gives me a rough estimate of what my hand would look like, disregarding the actual gameplay. And I can build buckets of those cards that would maybe group together something like what I've shown up there. Like it doesn't really matter which kind of 2s you have, if it's spades and hearts or the other 2. Or for instance, it could group 8-10 suited in spades with a 10 offsuit, right? So this could be a plausible clustering to do, but you need something more advanced, right? And once you have that, the game is much smaller, right? And then suddenly it becomes feasible to apply a counterfactual regret minimization. And what you do is you compute something they call a blueprint strategy that you learn entirely through self-play. So this Pluribus system in stage 1 plays against itself, and it does pretty much exactly the same exercise we just did with Kuhn poker, right? Play back and forth. One is the traverser, updates its weights, and then we go back and forth. And through self-play, we get a really good or decent blueprint strategy. So, and the authors mentioned that it costs only around, well, it might look much, but compared to other systems of that complexity, it's actually not. They used 12K CPU hours and 512 gigabyte of memory. And yeah, as I mentioned previously, it costs around $150 on the cloud, right? This is pretty impressive. Right. So what does the second phase look like? This is a bit difficult to explain in detail, so I won't, but I can give you an idea how it works. The blueprint strategy is just too weak. You know, we use those abstractions, right? So we group similar hands together, we group similar actions together, but this is just too coarse a strategy. This would never play in. This would never be play at superhuman level, right? But what we can do is, at least in the very first betting round, we can play the blueprint strategy if suitable. You know, if my opponents raise close to my abstractions, I can just round it off and say, all right, this is what I know. I play what I know from the first phase. And otherwise, you just drop this altogether. And what you do instead is you apply a technique called nested subgame solving, or subgame solving at a depth limit also, to play against 4 carefully chosen opponents. Right? And what you do is you start with your blueprint strategy, so the bot you build in the first phase, and you build 4 variants of it. You take the blueprint strategy itself, one that is biased towards raising, one that's biased towards calling, and one that's biased towards folding, right? So, and even if those 4 bots aren't exactly at superhuman strength, they're still pretty solid, right? And what you do is you play whatever you do before, but you randomly assume, and you don't know beforehand, at each betting round, you assume one of the 4 strategies, and you don't know beforehand. And you play against an unknown strategy of your opponent, and play it until the end. And then you update your beliefs about what happened in a way that's very similar to what we've seen in the first round. So it's a kind of counterfactual regret minimization in itself again. All right. And one thing you should also understand is that in this real-time search phase, what Pluribus will do is it will not just assume its own cards. Like, to give you an example, maybe I clearly hold the strongest hand, right? So I hold aces and I just hit everything on flop, turn, and river. So I clearly dominate the game. If I were to just raise the hell out of it, that would look suspicious. So what Pluribus does instead is go over each combination of private hands that I could hold myself and computes a strategy that it would play in this situation and carefully balances it out so that it doesn't look suspicious when you do an actual action. Right? All right, and then one question that might come up is, Pluribus constructed this way plays in a way that does not try to exploit opponents. All right, and it does so not to be exploitable itself. Right. So on the one hand, that means that you don't really crush weak opponents, but on the other hand, you also don't actually lose anything in expectation. So you also fare pretty well against really strong players, but you may not crush beginners as hard as you could, just to not make yourself exploitable to such attacks, right? And the second phase is even more impressive when it comes to hardware requirements. So the second phase runs on just 2 CPUs and a memory footprint of 128 gigabyte, which is something you could afford at home. All right, let's see a demo. So I'm going to show you something we built internally. So we try to replicate Pluribus as faithfully as we can. We're not as far as we would like to be, of course, but at the very least, we have a few things to show, right? So let me click on this demo. All right. So what you see here is a selection of 6 players that would sit on a table. And I make one of them a stronger bot. So this is a Monte Carlo tree search bot. That is the strongest one we have and know works, you know. And if we start this, our internally used debugging UI will open, and you can actually play a few hands of poker here. So you get a few stats and can kind of investigate if something fishy is going on in the system, right? So what I can do here is the first player is Max in the bottom. I don't know if you see that. No, it's not. It's the guy in the top left. But I can click through an actual simulated game of poker of 6 bots that we created. And you can test how well they play against each other, right? So I can click through. So, for instance, you see the one Carlo, as in Monte Carlo, he folded, right? I don't know if you can see that, but it's this red symbol up there. And so I can just further click through, and then you see the 3 public hands on the board. And yeah, let me just go through the game further and see who won in the end. Right. So we made it to the river, and there's a showdown, and you see that the top player called Monty and the top left player called Para, they split the pot because they both hit the ace. Right? I hope you can see that. All right. So this is a nice demo to play around, maybe. Well, what we can also do is we can simulate a bunch of hands, and because the Monte Carlo tree search bot is a little resource hungry, we just play 10 hands for now. Right. And maybe we see that he wins a bit. Well, let's play another 10 hands. Okay, all right. This is good. So, I mean, this bot on the right is really strong. So it will crush all the other opponents eventually, right? So, and it's also on top right now. Okay, cool. So this is what we use internally for validation for a bit. And then like the last part I want to show you is we also have a little debugging tool here, or like an evaluation tool if you like, where you see several bots playing against each other over time, and we'll plot the amount of cash they won against each other, right? So if they're below the line, they lost, and the pink bot here over there, this guy makes a lot of money from the other ones, right? All right. All right. So conclusion, yeah, we're not quite there yet. Like it's still an open question if we can make Pluribus work, if we can replicate a system like that. But it's useful to stress the point again that techniques like counterfactual regret minimization are powerful general techniques that we can apply to other domains, right? But efficiently doing so and implementing this is really hard, yeah. And so a question I want to raise to you, all of you maybe, is can we maybe find a common framework that solves all games, right? I mentioned that the techniques used to solve chess and Go don't have really anything to do with what we're doing here. So can we find a common game AI framework at least that solves all perfect and imperfect information games at once? And then also, can we apply those techniques to other domains as well, right? Cool. So, thank you.
Hi, Max. Thank you for your talk. So I'm going to ask you a question. How do you make money with this?
All right, perfect. Can I get the slides back? It's the kind of the obvious question that last time I spoke about that didn't come up. So let's see. So I just want to talk about really quickly how you build a poker bot at a high level, right? So you need like a fast gameplay. So we did all of that. So I was kind of lying to you. I said it's Python, right? What I do, but by now what we're doing is all C++, right? So you build this poker bot that is really suitable for such search tasks, and you do it well, right? And then you have to implement all of that and have sufficient hardware. That's kind of a given, right? And so what you have to do to well, if you wanted to make money with it, there's a few ways of doing that, but you need this just strong poker bot first. But what you can definitely do is do some screen scraping, maybe in a virtual machine, and read out the game state information that you have in common poker platforms, right? Because you need to get your hands on on your information that you have access to, and then you do some sort of basic computer vision to access the game state, and you need some way of controlling the mouse to feed that information back. And all of that is possible. There's like one open source framework that does that for PokerStars even. It doesn't fit in with our framework yet, but this would be something you could do. And of course, you could also just take your bot and use it manually, right? Nothing would stop you from doing that. Right, and of course, I mean, maybe the last one here. You should know that on most poker platforms, bots are, well, largely prohibited, right, by terms of conditions. It's not, I mean, it's an open question how illegal it is, really, right? But mostly what they disallow is like collusion, where you read out private information from other bots, and essentially cheating. But like stuff like stats tracking is not only fine, but mostly accepted. Like most professionals, semi-professionals play with stats tracking tools by now. And they will try to get you, but I think what the poker platforms do to catch bots is not that impressive. But you also have to say with a restriction that there's also not so much you do, right? I mean, you enter a raise amount and you click. So, yeah.
Okay, so let's get the questions from here. Do you think poker is harder for AI than StarCraft with fog of war enabled, incomplete information?
Well, I can't really say. Like, it's a completely different setting. But yeah, I thought about this as well. Like, I think they did 2 versions, right? StarCraft Fog of War enabled and then kind of accessing the API under the hood. And they had similar results. But the thing is that in StarCraft, I believe in the last version, what they definitely did was placing huge restrictions on the maps and the amount of races you could have and how this would play out. So I think if you do this in general and do like the true Fog of War version, I guess that would be more complicated. Definitely.
So during training, does it play against its same version or all previous versions? Or what is the strategy here for best training?
All right. Yeah, during training, it updates itself, right? So we said that in this form of counterfactual regret minimization that I mentioned, that's called Monte Carlo counterfactual regret minimization. So it's I fix one player that I update, and the other ones are essentially Monte Carlo or random players that play at the current strategy. And then I update myself, and then it's the next guy's turn. And so they update in well, round robin, so to speak. But it would always play against the latest version that's available.
Oh, this is a good one. How do you know how many atoms are in the universe?
Don't ask me. Ask the physicists. I don't know.
Any physicist in the room?
I never questioned that, actually. So, I mean, it's a good one to challenge, I guess.
It would be super cool to be able to play against it or the real Pluribus online somewhere and to see how strong it is.
Yeah, I mean, it's difficult to derive a question from that, but yeah, I see what you mean. I'm also looking forward to this. I mean, that's why we're trying to build a system. In how far we can make it public or like share it, I don't know. It's a little, I don't know, dangerous as well. Like if we succeed, in fact, then would have consequences on the game of online poker, right? But at the very least, because our initial Python implementation is so slow, maybe we can give you a toy version in open source at some point.
More. Is OpenAI suitable for poker? Did you take a look at it?
No. Sorry.
How many people worked on getting the boys to the current state?
The boys. The bots.
The bots. Okay, the bot.
How many
people? How large is your team?
All right. Yeah, there's actually 3 of us by now. So it started with just me, and now we have Mark Schmidt, who should also be in the audience. He contributed large portions of the C++ and the GUI, and Thomas from London, who has been a semi-professional poker player at some point, so it's kind of a good match.
Okay. Cool. So I think if you have any more questions, you can hunt Max down. He's in the building today. Right?
Thank you. Yeah.
Cool.